Hi, it's Tim, and today I'll be showing you how to use Simulink to simulate TIMs, and we'll be going to be using Lab 2 as an example. Okay, to start us off, we're going to scroll down to our first block diagram, and we're slowly just going to implement step by step it in Simulink. So first of all, to start, we're going to be looking at a sine wave. So I'm just going to double click on the schematic and type in sine, and I'll use the sine wave from the DSP system toolbox. Okay, so if we used the other sine wave, we can see here it's a continuous, so it's a smooth line, whereas here it's been sampled. And we're always going to be using the DSP ones in this course. So I can first double click on it, and that'll get me into the properties. Amplitude, I'm going to leave at 1. Frequency, I'm going to set to 2 kilohertz. So we'll always use scientific notation, 2 times 10 to the 3. Phase offset is at 0, and then sample time. So first of all, we'll get into some sampling fundamentals. To sample any signal, you always need to sample at 2 times the frequency. So in this case, it would be 2 times 2e to the 3. Oh, sorry. Oh, we'll just make this 4e to the 3. And the sample time is actually the period, so it's going to be 1 over that frequency. Okay, so we'll just press OK for this. The second block we'll use is our scope. Great, so we'll just align that, and then to draw a wire, we just need to click the input and drag it along to the input of our scope. Okay, so up here, that's the simulation time. So usually we aim, as a rule of thumb, to go for about 5 periods. So in this case, if we look back into our sine wave, our frequency is 2 kilohertz. So that means our period is half a microsecond. So we go 0.5 e to the negative 3. Not a microsecond, a millisecond, sorry. Great, so hopefully that's all looking in order. So we'll just press on the scope. And then we have 2 options, either we can press play in here or play on the schematic. Doesn't make any difference. Okay, so here we go. So we see that it does have 2 samples. So for this frequency, we can see the sampling is happening at twice the frequency. So technically it does maintain the frequency of our wave, but I think we can do a lot better. So first we'll try going for what I usually go for, which is just 10 times the frequency. And when we simulate that, we can see that there are 10 samples over the sine wave. So we'll go here, and we'll actually usually go for about 10 periods just so we get a good view of the wave. So we'll simulate that once more time. And now we can see we can have a really good sinusoid. If we wanted it to be even better resolution, we could go for maybe 100 samples per period. And we can see from here that it's quite smooth. But if we zoom in, we can see those samples as they make their way across the wave. Okay, and one more thing with that sample time, what we also can do is, instead of writing our sample time here, we could just copy that here and write in our MATLAB sample time. We'll make a variable equals, we'll paste that, we'll press enter. And that means our sample time is now saved in our workspace. And here we can just write sample time. Okay, so we can see it's here in our workspace. We'll click OK. And if we run that, we'll see it runs the same. And then if I change that sample time back to 10 times the frequency, it should automatically update that for us. Okay, so one more thing is that if I right click on this block, so first things I can do is I can comment. So I can comment through or comment out the block, which means it won't run. I'll just uncomment it here. And I can actually display the properties. So I can go in here. Where is it? Properties, great. I can look to the block annotation, and then these are all the parameters that are within the block. So if I want to display them, let's say I go down to frequency, I'll click this button here, or equivalently I can just copy and paste that here, and I can enter some text. So this is the example syntax, so we'll use that. So I'll write frequency equals this value. So I'll hit apply, okay. And now we can see the frequency pops up under there. And if again I go to properties, and let's say I want to display now the sample time. So here I'll just copy, paste it. Okay, and I'm going to hit OK. But here it actually doesn't really give us useful information because we have sample time loaded in our workspace. So it's up to you. Usually what I do, because sample time is actually going to be shared amongst a lot of blocks, I usually define that in MATLAB, but usually I define the frequency in the block so it's easy to click in and always change it. Okay, so I'll get rid of this scope and we're just going to implement the rest of this. So we want this to be m cos omega mt, so I'll just delete the scope, and what I'm going to add now is a multiply. Okay, so I'm going to join that here, and this is a really visual way of showing what they gain. So right now I'm going to set this to m equals 0.7. Okay, so I'll put up our scope. I'll just put it down here actually, just so we can see how it changes. And we'll just run this again. And now we can see it as an amplitude, a height of 0.7. Great, so the next block we need to do is an adder. So I'm just going to search add. Here we go. So now I'm just going to delete this line. So we're going to add here to 1 volt DC. So I'm just going to use a constant block. Don't worry about remembering all these blocks. Just either search for it or come and refer to this video. So I'm going to connect that constant block, and because it's 1 volt DC, it's going to display 1 volt here. Again, we'll do this step by step. So we're going to check on the scope how it looks. Okay, so now we can see that there's been offset to 1 volt. If we want to compare this to our original wave, all we need to do is hover our mouse here until we can see that plus sign, or we can right click on this and, I think we can right click on this and add 2 input ports. And simply we're going to drag a line here back to our first signal, rerun it, and now we should see the 2 signals superimposed. And if we click view here, we can click on legend, and that will let us toggle each signal on or off. So I'm just going to put the scope down here just so we can quickly refer to it. Okay, so we can see the next signal we're going to need is a multiplier. So I'm going to look up a product. The only difference between a product and this multiplier is that the product multiplies 2 inputs. We'll get rid of this wire. So this is our first input. And now we see we actually have our carrier signal. So what I can just do is I can just copy this, Command C, and paste it, Command V. I can hit Command R to rotate it. And I can use another multiplier. Rotate that once again. Great, and I can wire these all together. So we see our gain here, our AC, we'll just set that to 1, and then we'll change this frequency to 200 kilohertz. Okay, but this is going to give us an error if we run this, so I'll just connect this out. If I try to run this now, oh no, it won't give us an error, but essentially we see this product is a flat line, and that's because we're sampling this 200 kilohertz sine wave at only 20 kilohertz. So we can't actually get the information that's encoded in that waveform. So what we're going to do is we're going to update our sample time to 10 times 200 kilohertz. So that's 2000 kilohertz, which is 2e to the 6. Actually, I think this frequency is 100 kilohertz, sorry. Okay, so this would be 1e to 6. So refresh that. Now I'll run this again. And now we can see our signal. So here we can use this view box, and we can zoom in just to 1 period, and we can see this is a 100 kilohertz signal. And right now we have our sine waves that's been superimposed. So if we instead connect this to our envelope, which is here, We'll rerun this. And again, so I'll just scale out, and then I'll zoom into one period. We can see how this is providing the envelope for our amplitude modulated signal. Great, so we've done this first part of the lab. Just a note on the blocks we've used so far, in the add, we can double click and we can actually list different signs here, and that'll give us more input ports, just in case you wanted to change that. Furthermore, you can actually resize blocks if you'd like to make them bigger or smaller. And also with our product, we can double click on this and change the number of inputs for the elements we want to multiply. Great, so now we'll move on to the second part of our lab. So we're doing demodulation by first envelope detection and then coherent detection. Okay, so first what I can do is I can hit the spacebar to resize. I can actually zoom in on out, but I don't think there's any way to pan. So if you use zoom, or maybe these buttons to scroll around your schematic. Okay, so demodulation by envelope detection, we don't have a diode because this is strictly digital, so instead we're going to use the absolute value block. Okay, so we'll put in a signal here, and it's going to give us the magnitude of this. So if we connect that to our scope here, and we'll connect channel 2 to this output. So now if we run this, we can see if we zoom in, it's actually giving us the magnitude of that signal. And you'll note that's actually different from what we saw in the lab. In the lab, we saw 1/2, and then 0, then the other half, and then 0, because we were using a diode, which only lets current in both directions. So this absolute is actually giving us what we'd call full bridge rectification, where it rectifies the positive and negative parts of the signal, but that shouldn't affect our results. So we're also going to use our tunable low pass filter. So I'll look in here, filter, low pass filter, DSP system toolbox. So that's just my mum. Okay, so I'm going to pass this into our low pass filter, and again, we'll look at the output. And now we probably want to compare our original signal to our output to see the differences. So we'll look into our low pass filter, and I'll look at the filter response just so I can explain them for you a little bit. Great, so here we have our low pass filter. So as you can see, it has the cutoff frequency here, and then it attenuates all the signals below here. And note that this is in magnitude. So when it says the passband edge, so that's this red line here, any signal that you want should be within this passband. So in this case, we want to pass through our original signal, which was 2 kHz. So I'll write that as 2e⁻³. And our stop band is all the signals that we want to attenuate. So in a perfect filter, we would also write this as 2e⁻³, but any practical filter will have to have this part where the signal goes from the passband to the stop band. So essentially what we usually do, I aim to go about 10% of whatever our passband was. So in this case, it would be 2.2 kHz. So our maximum passband ripple, if we zoom into here, you actually see that this passband, this passband isn't quite flat. It has a ripple in it. Okay, so we want that ripple to be 0.1 dB, and that equates to around about 98% of our signal. Or to put it another way, if we had a 1 volt input, it would give us plus or minus 10 millivolts. Okay, so for our stop band attenuation, a stop band attenuation of 80 dB is actually quite small. It's actually 0.01% or 0.1 millivolts. So we probably don't need that level of attenuation, so I'm going to set this to 40 dB, and that will give us, for a 1 volt signal, around about 10 millivolts on the output, so the same as our passband error. So we're going to keep this sample rate, it's going to be whatever the sample rate we're using here is. So 1e⁻⁶. Great, and we're going to click apply. And then again, we'll view this filter response and we'll see how that's changed. And once again, we'll just view our filter response. Okay, you may have noticed that I just cut the video and now it's a lot less quieter, so my fans are usually the indication of when I've done something wrong in MATLAB. So I think this stop band edge, this 10%, was actually a bit too much for MATLAB to handle. So for now, I think I meant to say 10 times the amount. But essentially the stop band frequency we don't really know yet. So what we'll do, click OK here, and we're going to view our filter response. Now it's doing it, no worries. So now if we zoom back in, we can see that it goes from 2 Hz to 20 kilohertz. So it's a nice, and it goes from 0 to -40 dB. But we don't know what the stop band is until we have a look at the systems that we're trying to filter. There may be a big signal at 10 kilohertz that we want to filter out, so we don't know that for yet. So for now, we'll leave it at this. Okay, and that's passing back into our scope, so we should be able to run this now. Okay, great. So, okay, I've made a slight mistake, so we're not going to be doing our input signal, we're just going to be doing our offset signal. Great, and here we can see, so this is the output of our adder. We can label this if we want to. So we can label that signal as our, we'll call this the envelope. Okay, and then when we rerun this, we can actually see it's our envelope here. So we can see our output signal. We'll also add this input here. Let's rerun this one more time. Okay, so if we have a look at it, here we have our envelope, and that's our filtered response. Okay, and we can see there's a bit of a delay in our filtered response. So we can see it's actually delayed a little bit, and it's also attenuated a little bit. So if we look back to our low pass filter, when we look at view filter response, we can also look at the phase response as well. Okay, so here you can see actually that within our pass band, we say it has a linear phase response. Okay, so from 0 to 20 Hertz, we can see that it progressively, for higher frequencies, it progressively becomes greater and greater delayed. So we might be able to see that if we change our input signal to something like, let's say 1 kilohertz, maybe 0.1 kilohertz, and we pass this through, hopefully it should be a little bit less delayed. And we're going to have to increase this tenfold now. Great, and if we zoom in on this now, let's get rid of the product. So now we can see there's actually not as much phase, okay? So for lower frequency signals, there'll be less phase shift. So that's how our phase response can be visualized. So we'll just change this back to 2 kilohertz. Okay, we'll change this back to 5 milliseconds. Great. And now we'll move on to the next part, so demodulation by coherent detection. So we want this, another multiplier here. Sorry, product, I always get the two confused. So we'll place our product here. We want this 100 kilohertz carrier signal, so we can just actually cheat a little bit and use the same signal there. Just drag these down, so you can click and drag as much as you want. Great, and we'll take, so this is our carrier message here. Great, okay, and then we also want this to come through a low pass filter, so I can just copy and paste this low pass here, connect them. Cleanliness is key, okay, so we'll put that into there. And then because we've already set up this low pass filter, everything should be the same. So we'll run this one more time. Great, and we'll just... So this is where it comes in handy to label things. So now we've got our two low pass filters and we can see they're mostly the same signal. Okay, so we're coming to the end of our lab, but what we want to do now, we've been looking a lot of our scope, but we also want to have a look at the spectrums. So what I can get is what we call a spectrum analyzer here. Okay, so we can see here all of our signals are overlapped on each other. So we can actually go into Tools, View Layout, and we can actually separate that into 4 different views. Okay, so here you can see these are our two outputs, a low pass filter and low pass filter 1. So we'll actually just rename these signals from within here. Okay, and now we'll get the signal analyzer into play. So we'll uncomment this. Okay, so we'll double click on this. Okay, and we'll just run the simulation again. Great, okay, so what I'll do is I'll go into the settings of the spectrum analyzer just to make sure everything's set up correctly. So our sample rate, we want to inherit this from our input signal. We want to view the spectrum. Our type will be RMS voltage, and we'll go for full frequency span, so that'll just go through it all. Units, this should all be correct. We'll just do a one-sided spectrum, but your two-sided will just be flipping everything over to the other side. So I'll click run on this again. Great, okay, and I'll just full screen this. Awesome, so what we can see, we'll just have a look at our legend. Okay, so this is our product. So first we have our input signal, which is around 2 kilohertz. And then when we multiply it with our 100 kilohertz signal, we zoom in now, we can see that there's a spike at our 100 kilohertz with our two sidebands, each at plus or minus 2 kilohertz. Okay, so we'll zoom back out of that. Okay, and then once we perform the absolute value of that, we can actually see that we get this, we still have this component of our original signal, which is the same as our envelope, but we also get these copies that are produced, these higher frequencies. So what I want to do is I just want to show what the output now is from the multiplier. As you can tell, my computer's struggling with this a little bit. Great, okay, so we can see the multiplier. Again, it shifts everything back here, and it also gives us copies because it's multiplying by that 100 kilohertz again. Okay, so the second part of the lab asked us to change the modulation index to 1.5. So we'll change it here, and now we'll run this whole circuit again. And we'll just zoom this to fit. So now we can see there's these overlaps in our signal. Okay, and we can see those overlaps are actually reflected here. So we'll go full screen on this again. We'll actually go full screen on both just so we can have some good looks. Great, so we see there's still no error between our envelope detection and coherent detection, but if we look back at our spectrogram, and we'll just restore view here, we can actually see that our envelope detection, that's the green, is actually giving us these multiple frequencies as they're going off, and our coherent detection isn't actually giving us, so that's the red here, the product. Okay, so how we can view that is when we're defining our low pass filter. Remember we said the cutoff was 2 kilohertz. So now we'll try expanding that cutoff frequency to maybe something like 5 or even 10 kilohertz, and we'll see if that affects our output signal. So what we'll do, we'll go into these filters and we'll set them, instead of being at 2 kilohertz, we'll set them at 10. So we'll keep this at maybe 20. Again, we'll go to 10 and 20. Great. And we'll run this again and see what happens. Great, so our frequency spectrum is still the same, but now you can see on our envelope detection, because our envelope has introduced these extra harmonics, they're actually being reintroduced to our signal, whereas the coherent detection, which is here, the red, so we'll just put up, so this is the envelope detection and that's coherent. Okay, so you can see how down in this corner and here, we're getting these harmonics, which can actually corrupt our output, and that's why coherent detection is usually valued. Great, so we've gone through most of this lab. The demodulation of unknown signals and the speech signals I'll cover in another tutorial, but hopefully this should get you all set up on all the types of blocks we'll need for later labs. I hope this helped. So in this lab, we looked through lab 2, and we had a look at a couple of the different blocks and how to analyze them using the scope and the signal analyzer, and I'll see you in the next one. Okay, bye.